In this video, we'll be taking a more in-depth look at Pearson correlation. Pearson correlation is the most common of the correlation methods. You can find information in our book on Pearson correlation on pages 206 to 208. If you do not have the book, just continue with the video to find out all you need to know about Pearson correlation. Named after Carl Pearson, it makes use of interval and/or ratio data only. So X must be interval or ratio and Y must be interval or ratio. A Pearson correlation is a great way to illustrate the use of z-scores to convert two disparate scales to the same scale. We will illustrate this in a few minutes with the example we will be using. Computing a Pearson correlation on interval or ratio data is very formulaic. The guide to this approach is contained in the Pearson formula. Let's take a moment to dissect the formula. When doing a Pearson correlation, you will need to collect your X and Y data. Note that the formula says that you will need the sum of each. The formula also says you'll need the sum of X squared and Y squared. To get the sum of X squared, we simply square each X, then add up those squared values. We then square each Y and add these values. This gives us the sums of the squares for X and Y. We also need to square the sums of X and the sum of Y. To get the next two highlighted terms, we then need the sum of X times Y. This is not, repeat not, obtained by multiplying the sum of X times the sum of Y. Many people make this mistake. The sum of X times Y is obtained by taking each individual value of X multiplied by its individual paired Y value. The last term we need is N. To get N, we simply count the number of subjects in our data. To guide us through using the data, we will construct a table. We will end up with 5 columns, one each for the terms just presented. Only the X and Y column will initially have data. We will derive the data for the other columns following our formulaic approach. In this table, X is height in inches and Y is shoe size for 14 U.S. presidents. These are your collected data. We want to know if there's a relationship between height and shoe size. To do this, we first compute the sum of X and Y. We now need the X and Y squared column. We square every X and then sum. Now we do the same for Y squared column, squaring each Y and summing. Our last column is the XY column. Multiply each individual X times each individual Y, then sum. This gives us 5 columns of numbers and 5 sums, one for each column. We simply substitute these sums in our formula and crank out an answer. When we do this, we find that the correlation coefficient is 0.85. But what does 0.85 mean? Using the Pearson correlation table for n minus 2 degrees of freedom, in other words 14 minus 2, we find that at the 0.05 level, two-tailed, the critical R value of the table is 0.532. If our computed R is equal to or greater than the critical table value, we have a significant correlation, meaning a significant relationship between height and shoe size for the 14 subjects. Since our computed R of 0.85 is equal to or larger than 0.532, we have a significant result, not a chance result. Equally as important as the table value is the square of any significant computed correlation coefficient. This is called the shared variance, or the effect size, or the coefficient of determination. What it indicates is the percent of underlying variables that the two values X and Y share. If we square 0.85, we will get 0.7225, or 72.25%. If we can think of all the factors that influence height, such as genetics, parents' heights, nutrition, and so on, and find the factors that influence shoe size, such as genetics, parents' shoe size, wearing shoes as a child, nutrition, and so on, then about 72% of these factors are common influences on both height and shoe size. That is, it shares factors. In the real world, finding a correlation where there is a 72% overlap is common factors is really good. It is a strong finding. So why did we use the 0.05 level in the table? Generally speaking, the research of this type, keeping chance occurrences at less than 5 times out of 100, is a tight enough control on chance. In medical research, where lives may be at stake, the controls might need to be tighter. And why do we do a two-tail rather than a one-tail? Simply because it is more conservative, given that correlations tend to be weak statistical procedures and therefore prone to significant findings spuriously. What about our findings? They are significant and even account for a good deal of the underlying common factors between height and shoe size for the presidents. Are these findings meaningful in that they add important research information? Probably not, but it was fun. We mentioned the use of z-scores to get two different variables, in this case height and shoe size, in the same scale for mathematical purposes. In the diagram, you will see the same height and shoe size data. Note that there is now a column for the z-score of each x, or each height. There is also a column for the z-score of y, or each shoe size. And there is a cross-product column where each z-score for height is multiplied by each z-score for shoe size, paying close attention to positive and negative variables. When we sum the cross-product column, divide by 14, we get the correlation coefficient of 0.85. Simple, right? Just briefly, and your instructor can explain further, note that a minus times a minus yields a plus, and that a pattern set up with the signs from the cross product such that cross products are positive, meaning if a president is above the mean on x, they are most likely above the mean of y, or if below the mean on x, also below the mean on y. Also note, we can multiply z-scores. Multiplying Lincoln's height times his shoe size gives us 1064. Makes no sense whatsoever. Thus, the utilities of z-scores. Thanks for watching, and please check out our YouTube channel for more videos on statistics and research methodology.